For more problems and videos like this for linear algebra, you can take a look at Sarai Studies. Link is in the description box below.
We're told to determine whether the following subset, so this is a subset of R of n, so some vector space, they're telling us specifically that that vector space is R2. We want to know if this subset is a subspace of that vector space. So just to give you a picture, let's call this box a vector space of R2. And we know it is a coordinate plane.
And we know that the subset is something inside that vector space, that box.
So then the question is this subset H a subspace? And then you'll be like, okay, well, a subspace is just a subset that satisfies the conditions of a vector space. And then you would go on to check your conditions. The first one is 0, an element of H. So if this is H right here, and you can plug in any real numbers for X and Y, if I plug in 0, that would be 0 times 3, that would give me 0, 0 times 2, that's 0. So this is an element of H, so we just checked that. But then for the other two conditions, we would have to take two vectors A and B, or just 2 points in H, add them, and find if their sum is an element of H, so if it's inside H. But since X and Y can be any real numbers, we can pick literally whatever. We can do 4 and 2, and then with 4 times 3, that would be 12, 2 times 2, that's 4. And so because it's something that we got from this is also in H. And you'll keep doing that and you'll realize, wait, every time I plug in any value in here, whatever I get is going to be in H because that's the definition. And you'll be like, oh, that's great. So it satisfies the conditions that when I add two vectors, their sum is in H. But remember that has to be true for all vectors in H, all of these points in H. And you can't possibly prove that. That's infinitely many points. So when you come across a situation where you're really confident it's a subspace, but you can't just use the conditions of a vector space
because you don't have forever,
then your goal or your strategy is to define H as a span of vectors.
And I'll explain why, but first I'll explain how. And the strategy is if you have something like this, to write this in vector form.
Think of it as factoring out the x and the y's. If you have two variables, you factor out the x, leave an empty bracket, always plus, then factor out a y, leave the empty bracket, and then ask yourself, what was attached to my x here? It was just a 3, and then there was no x here, so it would be 0. So 3, 0. Then what was attached to my y? Well, here nothing, so 0, but then here there was a 2. So 0, 2, and this is the same thing as this. This here is your subset. This is really saying that the subset is just a combination of these two vectors and whatever these are. And there's infinitely many values we can put in here because x and y are all real numbers. We can literally put any real number in here. So that means that H can be any combination of these two vectors with whatever real number we put in here. And that sounds familiar because what is another way that we can express all of the possible combinations of these two vectors? Well, if you remember, we have something called the span. So the span of these two vectors is really just saying, hey, take all of the possible linear combinations of these two vectors, and that is going to give you H. And so this is what it's talking about. Find a generating set for that subset. If it is a subspace, these two vectors, when you span them, I like to think when you scale them with whatever scalars you have here, whatever variables you can put in here, it says that we can put any real numbers. The results of those vectors, all of those possible vectors are going to span H. They're going to generate H. They're going to create H, however you want to say it. And by definition, by a theorem that we have, a span is a subspace, and I'll prove it to you. So here's your official theorem. First, let's kind of review. This is just a coordinate plane. It's the second dimensional space of all real numbers. We know that we can call that a vector space because we can represent points as vectors as well, assuming we're starting from the origin. And remember that a subset is just something inside this vector space. So it could be this point, this vector, these are vectors as well, anything. But then a subspace is a subset, so something inside this box, that's what a subset is, that is also a vector space. In other words, it satisfies the conditions of a vector space. So I am telling you that this subset is a subspace, and I'm calling it H. So that's what I'm telling you. It's given to you that this is a subspace of V. So in other words, this subset satisfies the conditions of a vector space, so therefore we can call it a subspace of V. Now let's look at what the theorem says. The theorem says that if you have just these vectors inside V, so you just have these vectors inside V, this box, then all of the combinations of those vectors is a subspace of this box. So let's translate what that means. So we're saying that H, which is a subspace, is really the combination of these vectors that are inside V. But what's another way to say vectors that are inside V? Remember what a subset is just something inside V, the vector space V. So this we can translate to a subset. So we have some subset, and it's saying that all of the combinations of this subset, right, it's just a collection of vectors, is a subspace of V. And then the question is, what's another word we can use for all of the combinations? Remember that the collection of all linear combinations of vectors is called a span. So in other words, for every single subspace that you have, there exists a collection of vectors, let's say vector 1 from vector 2 to vector n, inside this vector space. And if you take all of the possible combinations of those vectors, meaning that you can scale them, you can add them together and get other vectors, all of the possible resulting vectors, all of the combinations, that's what the span is. If you take all of the combinations of those vectors, that's going to give you H. It's going to generate H. It's going to span H. I like to think of span as like scaling. If you have this collection of vectors and you scale them, it's going to scale to H. So for example, let's say you just have these three vectors, this vector, and maybe this vector. So these here are your vectors. It's just that this is V3. So you have three vectors. These three vectors right now are just a subset of V. They're just something inside V. That's the definition of a subset.
It's a collection of vectors inside V.
If we take all of the possible combinations of these vectors, in other words, if we take this vector and we just scale it, like with scalar equal to 15, and then maybe we take this blue vector and we scale this one to 15, then we literally have H. It spans H. The combination of these vectors span H. They generate H. They literally form H. So the theorem says that for every single subspace that you may have, there is a collection of vectors who will combine, who will add together, who you can scale to generate that subspace. And so by definition, a span is a subspace. And so if H is this, and we can rewrite this as this, and then we can rewrite this as this, then H is that. So H is considered a span of these two vectors, just all of the possible linear combinations of these two vectors. When you scale and add these vectors in the infinitely many ways that you can, those resulting vectors, all those combinations of these vectors will generate H. So by the theorem, we know that a span is a subspace. So if we can define H as a span of two vectors, then we know that it is a subspace. Then we can say that is a subspace.
And that's it for this video. I'll see you in the next.